about Const. Well, if you are introduced to Const at the first time, it might look like one of those funny data types that has not really that many use cases, just there because we can do it. But surprisingly, there are a lot of useful use cases that are not obvious. So this talk will show you some of them. There are probably more. If you have more interesting ones, just let me know afterwards. Okay, so this is the whole definition of the Const data type. It's just a new type that has two type parameters, A and B. And as you can see on the right-hand side, you will only ever be able to get an A out of this const AB. That's because the B is the so-called phantom type, and it's just a tag that is attached to the A, but you will never get a value of this type. Okay, so you can also think about this as a type level version of the const function that is also present in the prelude, which is also named const, so don't confuse those two. We are talking about the data type. So in the rest of this talk, we will go into the functor instance for this data type, into the applicative instance, and also into the selective applicative instance. Let's start with a functor. So here we can say instance functor, and then we have to partially apply the const with the first parameter A. And then we have to define the fmap function. And here is a hole, and GHC will tell us that I found a hole here that has to be of type const AB. And you have relevant bindings there, which is the function we are mapping with, which goes from A1 to B. And we have a value of type C. So this is the one that we bound with the add pattern, which is of type A and A1. So now we have a problem because the function wants an A1, but the const data type has the A1 only as a phantom type and only has a real A in there. So there's nothing we can apply F2. But we need to somehow produce a const of AB because that's the type of the hole. Well, so what do? Well, we can just cheat because we can unpack the A from the const and repack it, and the phantom type will just adapt to whatever we would need. So what is this doing in the functor case? Well, there's a GHCI example where we have a const value that has the first type string and the phantom type int, and the actual string inside the const says you can touch me. And if we fmap over this with a +1, which matches the int phantom type, we still get back the const with a can touch me. And we can also fmap with anything that matches our type, so for example print, but it will just do nothing. We'll adapt the type with a new const wrapped value, but it still is a string you can touch me. So that's what it does, but why is it ever useful? So if you look at the lens libraries, this is a simplified lens type. And it's a function that is parameterized over a constraint with a functor over a higher kind of type f. And then you get a function that goes from a normal b to an b wrapped in this f. And you're also given an a, and you have to produce an f of a. So you can think about this a as some larger type that we have to get out a b, and then we will modify it, and we get back a modified a in this fa. And let's define the _1 lens, which gets out the first component of a tuple. So what we do is we fmap over the tuple, we apply the f to the first component, and then we wrap it back up with the second one. So the second one, the y is never changed, but the first one is put through this f function. Okay, and now comes the trick. For this lens, we want to define the getter. So the get method. Here we are. So the get method gets in a lens. So this is this one here. That goes from A to B. And then we are given an A, and we have to extract the B. And the trick now is we can apply this lens to const and to x, and then we can unwrap the const again. And then we have our getter. So how does this work? Here's the equational reasoning for that. So we pass in the _1 lens to the tuple. Then we can inline the definition of the get function. So we have get const and the _1 applied to const and the tuple. Then we can inline the definition of the _1 method to get back this fmap case. Then we can remember that the fmap for consts just does nothing. So we can rid of the fmap, and we are left with just get const of const 42, which just unwraps the 42 again, and now we have our getter for our lens, just by using const. Okay, so it was useless at first glance, but it's really nice for lenses. So that was the functor instance. Let's go to the applicative instance. This was probably one of my favorites for Const because it opens up a lot of possibilities. And it does so by connecting two very important concepts. Okay, so here's again the instance for the applicative. And again, there are two holds. So we need to implement the pure, which given an A creates a const of some MA, whereas the A is just a phantom type. So whatever A we get, we will not be able to use it for anything because it's just a phantom part. And for the app case, we will be given two consts that have some phantom type. The first one is a function, the second one is a value. But again, we will never get a real value out of this const that has this type. So what we are left with in the app case is just two m's, and we have to produce a third m. Okay, so we have to produce an m from nowhere that calls for monoid. So we add a monoid constraint to the applicative instance and use that one to wrap it up in const. And for the app case, we just apply both of our values using the combine method of the monoid. Okay, that was the instance, but what does it mean? Well, this means we can use any function that takes applicatives, and we can just sneak in some monoids in there wrapped in const. So for example, if you look at the traverse function from traversable, we can apply this with const, and what we get back is essentially a fold map, because you will get back a const of mb, so we can ignore the b, and at the end we will get a const m and the traversable structure of b, which will just be lost, and we will only get back the monoidal result. And if you look closer, well, this is just the fold map case from the foldable type class. That's why traverse is enough to also derive an automatic fold map implementation for you. You can also use const to statically analyze free applicative programs, or if you have seen the build systems a la carte talk, you can also use it there to statically analyze applicative programs. So you can run your program without executing effects, but just accumulating some monoidal result. Or you can even pair up an applicative with a monoidal value, because applicatives compose, and you can run it and at the same time accumulate some monoidal value. And const also beautifully highlights the relation between applicative and monoid, because if you plug it into the laws for the applicative type class, you can see that the laws also state that all applicatives have to be monoidal in their effects, which is very nice to see. I can only recommend to do that at home. Okay, so we've seen the functor and the applicative instance. Let's look at selective applicative functors. And this was one of the more recent papers which introduces another abstraction that sits between applicative and monads. And what it gives you is that while applicatives do statically determine the effects, and they are also executed statically, selective functors now allow you to execute those effects dynamically. Okay, so in short, they also offer some benefits of arrows, if you think of those, but arrows are a bit more powerful. But we'll not go into this in this lightning talk. So here's the selective type class that also comes with some additional laws that, of course, are not shown here. So, and what does the selective type class buy me? Well, I like to think of it as giving you the ability to branch on effectful booleans. So you have the ifs method below that says, given a boolean that is wrapped in an f, I have a then and an else branch, and whatever is the bool will determine which branch gets executed. Okay, and now the interesting part. How does the instance for const work here? Well, actually, for the selective type class, we have two alternatives to implement this. And for this, we define two new types called over and under, which are essentially const, but just wrapped. And we use over for static over approximation and under for under approximation. So if you think about the type class at the top, we have the first instance over, and in the select case, so the select has an effectful either value and a function from A to B. So it's either a left, then we can apply the function to get a B, or it's a right, and we already have a B, and we can just return it. So in the over case, we collect the monoidal value for the either in any case, and also the monoidal value for the function that is conditionally executed. So we will always collect both monoidal values. In the under approximation case, we only collect the monoidal value for the either. So if the either, for example, is the right and we never execute the f, we don't collect this. And even if it would be executed, we still don't collect it. That's why over also always goes into conditional branches for the if, and the under will always ignore them. Okay, so why is this cool? If you define a DSL using the free selective or some other approaches using applicatives, you can express conditional branching in your DSL, but you can still do static analysis, and you can do speculative execution, for example, and you can reuse everything that you know from monoids to do static analysis. And over and under are, for example, useful if you want to make sure that a certain effect always occurs. You can use the under approximation because you can check that it's not conditionally executed. And if you want to check that something never occurs, you just use over. And for example, you can make sure that no missiles are launched or something like that. Okay, conclusion. A new type is a very simple type that is nonsense at first, but has many very useful instances. You can also look at the monad instance if you want to. It's very useful because it tells you what the difference between applicative and monad is. And it's also a very good tool to understand the monoidal aspects of applicatives. So I think there's a lot more into Const that is immediately obvious. And that's all I've got. Thanks.
Probably squeeze in one question if anyone's got anything burning. If not, you could probably